I do receive research grant support from time to time from Alcon Laboratories. The immediate goal of a surgeon on table when he is removing the cataract, can I have the lights down please, is to really achieve a clear cornea immediately and day one. And nucleus fragmentation really plays an important role in achieving or not achieving the clear cornea immediately after the surgery. Now, when we remove the lens, and if you have a kind of a system in your mind of distinct phases or stages, when you remove it, it's a good idea so that you can handle all kinds of grades of nuclei and different environment in the eye. For me, most of the time it is the sculpting, creating a space. Having done that, next phase would be division, and that would be complete division. And once that is achieved, I move on to the critical phase of divided fragment removal. Now, why we need to do that? That each phase really needs different parameters because the objective of each stage is different. So if you have this conceptually in your mind, you will be able to perform more with control and produce a clear cornea every time. So regarding the sculpting, what we need to do is, having removed the viscoelastic from the lens, we can go for a continuous mode or an interrupted mode, but be careful that when you do this sculpting from subincisional to other part, your tip, the bevel, doesn't get occluded. You want to keep that open, because if it gets occluded, not only you rock the nucleus and stress the zonules, but you waste your energy. So pay attention and look at the bevel that it doesn't get totally occluded. Keep it open, and that also will allow the aspiration fluid to pass through and cool the tip and therefore the incisions. Now, once again, how deep you want to do, you don't need a very long tunnel like this. If you're doing a 4-quadrant technique, you can go peripheral, you should go, but you don't need to go extreme peripheral as I'm trying to show. But the depth is more important. And once you get this kind of red glow there, you know that this is good enough, whether you are going to separate or chop. So that kind of enhanced red glow would be an indication. Why suture are at 2/3 of the depth, so that all could be a good way of judging that. But make sure that you have some kind of understanding of the depth, either relate to the vice suture or increased glow, or if you have a slit attachment or oblique illumination, as you saw, that also will help you to determine how deep you are. Deeper you are, easier will be to separate or chop, and less forces to the bag. So that's thing. But even in a dense cataract, you don't need terribly long tunnel, because longer the space you create, larger, more energy and more heating and everything. But what is important is to really produce adequate depth in the area you want to begin your division. So I think these kind of examples to remember that long but not too long, deep is more important, and avoid occlusion at the tip, and keep sufficient flow rate so that the tip remains cool. Now, division, there are several techniques, but 4-quadrant technique still remains a very important technique. The difference now, and compared to the previous where some of us learned, is the flow rate and the parameters. Now, if you use flow rate like 14 or 16 when you go to this kind of softer cataract in the periphery, you don't need to do this, but I want to highlight that it's very safe to go even to the periphery using this kind of flow rate, 14 cc here, or a very low bottle height, but sufficient energy. This is a very soft cataract, so I'm using 40% preset. But the point is that the 4-quadrant technique of division is very good. There is nothing wrong, and many of these cataracts which are not, we are sure whether we can chop, one should, I believe, now go to the four corners straight away and use it very predictably every time, these techniques. So I think four cornering still remains a very useful tool. For the chopping techniques, there are vertical chops, the horizontal chop. It doesn't matter what you do. You could notice the paper was placed to the periphery and then brought to the tip. Now, one can rotate that and repeat that procedure of chopping on the other end of the space, so that you have a total division in one meridian and have two hemisections. So bury that thing, and when you bury this, you need to a decent energy here so that it doesn't get occluded here before you start doing it. But you don't need too much of it. Just need a burst of energy. I'm using the burst mode, and notice that flow rate is only 20 cc. But in no time that preset vacuum is achieved. Once again, the chopper is placed around the equator and brought toward the tip, and these dense cataract then can be separated with the help of lateral separation once you begin the chop. So it's actually a chop principle as well as lateral separation at the bottom. There are many techniques, and this is one of them, where you can do predictably with the chopper remaining within the rexus margin in the central area. You initiate the crack by vertical motion and then extend that crack by placing the chopper in the depth at various depths, bringing that towards the bottom plate. So that's a step-by-step approach, but the key is to continue division until the entire nucleus is divided. Why? One, because it keeps the back protected, but more importantly, the parameters for this phase division is different, like the very high vacuum. While for the next phase removal, you don't need that much of a vacuum. Therefore, you need to change to and fro different parameters if you divide and remove. So it's a bit tedious. So I suggest to complete the division phase and then proceed to the next phase. In a very dense cataract or a leathery cataract, sometimes one chop action, horizontal, vertical, is not good enough. And therefore, you need to repeat that chop action, whatever your chop action is. For example, I've begun this chop here, and it's so dense that if I want to extend that to the very depth, I really had to use so much of force. So notice, I took that occlusion off, and I'm reapplying it and burying it again at the same point, but at a deeper level. So I'm bringing the division force closer to the bottom plates, and that will be more effective and would induce less force. So you have various ways of chop, doesn't matter what you do, but the end point of that division is the multiple fragments, so that you can handle the segment removal phase, which is the most critical. With this will decide the corneal clarity or otherwise. And remember to use optimum irrigation and parameters, but more importantly, be conscious of the plane at which you remove the fragments. If you use less energy, for example 1 millijoule, but you remove these fragments near the cornea, like here, versus 4 millijoules but remove somewhere here, this will be kinder to the cornea. So plane at which you remove is also important in addition to the energy spent. And this exemplifies that this operation was done very fast and very rapidly with less energy, but the cornea was not clear, and you can understand why that is. Versus using viscoat before you begin. And I always paste viscoat near the cornea before I begin this phase of removal, irrespective of the density, and then try to be conscious of putting these fragments away from the endothelium and taking my time, reducing the parameters and the preset vacuum so that you can do that. Now, these kind of dense fragments can easily be removed with the combination of various technologies, interrupted energy, white star, and this is an example of ozil, which you can do it very rapidly and controlled way. And these kind of rotational or torsional ozil component, this high-speed photography demonstrates how that fragment remains repositioned at the tip, and the left-hand instrument is really stationary, doing nothing. And that fragment actually carousels into the tip, which is kept horizontally as well as directed to the posterior capsule, and that fragment, without any additional help, keeps coming. That's because the lens fragmentation process, which is necessary before you aspirate, is done in such a way that surface shears and there is no total occlusion, and that keeps repositioning into the tip. So I think the combination of these kind of technologies, the right optimum parameters, will allow you to confine your lens removal process into a very favorable position or a plane, so that you can predictably achieve clear cornea irrespective of the density or local environment. So that's is something, but this is something I want to finish it up with. What happens with the intraocular pressure when we use high parameters like 40 cc minute and 110 bottle height? You see this IOP, it's 80 millimeter and it fluctuates so much. So it goes very fast. You can see the procedure is going very fast, but the IOP is 80 plus and a lot of fluctuation. Versus this 20 cc per minute, bottle light 70, and the IOP is about 50, and it is more or less in a straight line. And then also, if you notice behind that sketch, the procedure is not very slow. It's a sufficient speed and efficiency that is going on, but the IOP fluctuation and impact is less, and that's because of the low bottle height and low flow rate. So I would think it's prudent to use low parameters as much as you can do, because the clinical impact also shows a favorable impact on the cornea. So finally, the devil lies in the detail, paying attention to every small detail. Each phase needs spatial attention. Each point of the time has a different objective and different performance. So thank you so very much.